Hello everybody. I thought I'll post this lecture note, basically a few examples that I went through in my real life face-to-face class, so I thought I'll share these examples with you as well. First of all, let me draw position versus time graph for two objects. So let's say this is time and this is position X, and the first object's position versus time plot looks something like this, a nice straight line, and the second object's position versus time plot looks something like this. So we call the first object A, the second object B. Let me ask you to think about this question. First of all, when do you think the velocity of object A and B are the same? Or the speed, if you only consider the one-dimensional motion. Is it at point 1? Is it at point 2? Is it at point 3? So 1, 2, or 3. If you like to think about this for a second, you may pause the video and then I'll give you the answer after you come back. So we have here a position versus time plot. As you know, velocity along this axis X is defined as the derivative of position versus with respect to time. So the derivative of a curve A, well, curve A is a straight line, therefore slope is constant. Object A is moving with a constant speed or velocity, and curve B has a gradually increasing slope, which means that the velocity of object B is increasing as time passes. So what you want to figure out is, when is the slope of B same as A? To do that, you figure out at what point is the tangent to curve B, which is that green line there. At what point does the tangent to curve B has the same slope as that of curve A, and that's point 3, of course. So the correct answer was 3. I know this is a simple example, but say sometimes simple things that we forget to consider. Now let's move on to a real example. What we have here is a ball which is released from a height of 1 meter on a frictionless 30-degree slope. At the bottom, it turns smoothly onto a 60-degree slope going back up. What maximum height does it reach on the right side? Now, before we actually dive into solving this motion problem, let me mention a couple of things about the buzzwords that you need to watch out for in physics questions. First of all, frictionless, of course, means there is no friction acting on our object, which means that there is no force, contact force between the contact of object with the surface. So there's no force slowing the object down. Smoothly means that although here at the bottom of the ramp we have a change in direction of the motion, the word smoothly means that forces can be neglected, forces that make the object turn here can be neglected. So for all intents and purposes, this problem can be considered as a one-dimensional problem, except we have these angles to consider, and the angles here merely affect the accelerations acting on our object. Now, what we have here for the first part is, well, we have, first of all, we have acceleration g, acting on the object. However, in the first part, going down the ramp on the left hand side, the object's motion is in this direction, so if we call this direction x, the acceleration that we care about is the component of g along x, and we can call this ax. And looking at the triangle, the red triangle that I have here, of course this angle is also 30 degrees, same as the angle of the slope, which tells us that our ax is equal to g sine of 30 degrees. Now you notice that our acceleration vector ax is pointing in the same direction as the positive end of our axis. Therefore, ax is a positive acceleration, and sure enough, as one knows, object A does accelerate or speed up going down the ramp. Now, on the ramp up, let's say when the object comes to stop here or anywhere along the curve, of course g once again acts directly down, and since the motion of the object is upwards, I'm going to choose my x-axis for the upward portion to be pointing up along the motion of the object, and in this case the acceleration ax acting on the object is once again the component of a along component of g rather along the axis, and in this case ax once again, this is angle 60 degrees. ax is equal to g sine of 60 degrees, with one big important difference, and that is that if you notice, ax on the ramp up is pointing away from the positive of the x-axis, therefore it's a negative acceleration, which means that on the way up one would expect the object to slow down. Now the question is, how far up the ramp does the object go? Well, to figure this out, we can what we like to figure out is if this is when the object stops, this is the maximum height. Let's call this h h2 if we call this h1. We like to figure out what h2 is. So similarly, let me call the acceleration on the way down ax1, on the way up ax2. So I'm calling everything down the hill 1s and everything up the hill in 2s, subscript 2. So let me write down the knowns. Let's say that we call this x0, or actually this should be x1 now. x1, and x1 I can call is 0 meters, so this position here I've defined as the origin of my x-axis on the way down. Okay, and of course my velocity one the object starts at rest is 0 meters per second. Now I can figure out what displacement the object goes through by using, well, first of all, the total displacement that the object is gonna go through you can tell by looking at this green triangle. I don't know if it's clear, but I'll try and do my best to. If you look at this green triangle, we have a right angle triangle which has a side of 1 meter, an angle of 30 degrees, which means that the hypotenuse here, the total displacement that the object goes through is so delta x on the way down, delta x1 is equal to 1 divided by sine of 30 degrees. If I'm not mistaken, sine of 30 degrees is a half, which means that delta x1 is equal to 2 meters. So that's the total displacement that the object goes through. That would give me, now I can calculate the final velocity that the object has at the bottom of the ramp. The final velocity that the object has at the bottom of the ramp, let us call this v2. This is position 2, that's position 1. So v2 is equal, v2 squared is equal to v1 squared plus twice the acceleration that the object has, we call that a1, times displacement, delta x1. v1 squared is 0, plus twice acceleration a1 is up here, which is, let me scroll down, which is g sine of theta, which is a half, okay, times delta x1, which is 2 meters, i.e. v2 is equal to square root of 2g. Now it's plus or minus, and it's up to you now to choose the right signage. Of course, the velocity at the bottom of the hill is still pointing in the direction of the positive x-axis, which means that v2 is equal to positive square root of 2g. Now that velocity square root of 2g meters per second is the velocity that our object has at the beginning of the ramp up. So when the object starts going up the ramp, its initial velocity is root 2g. So now let us see if we can figure out this displacement, the displacement that the object will go through on the up ramp. To figure that out, once again, let's use and let's call this position 3 at the top of the ramp. v3 squared is equal to v2 squared plus twice acceleration 2, because now we care about the acceleration in this area, times the displacement delta x2, the displacement up the ramp. Well, v3 we know is 0 meters per second because the object comes to rest, so that's 0 is equal to v2 squared is simply 2g from down here, plus twice, now acceleration a2 is negative g sine 60, so that's negative g sine of 60 degrees times delta x2, which means that our delta x2 is equal to, what is it equal to? That's negative sine becomes 2g divided by 2g sine of 60 degrees, I believe, if I didn't make any silly mistakes, or which is equal to 1 over sine of 60. And sine of 60 inverse is equal to 1.15 meters. So that's the displacement that the object goes through going up the ramp, but the question asked for h2, how high. So now once again here, let's look at this blue triangle. Up here we have a 60-degree angle, opposite side is h2, and hypotenuse is 1.15 meters, which means that h2 is equal to 1.15, which is the hypotenuse. So let me scroll down, I'm running out of space. So we have a triangle, it's a 60-degree triangle, hypotenuse 1.15, and we care about h2. h2 divided by 1.15 is equal to sine of 60 degrees, which means that h2, oops, I scrolled down too much, I apologize. h2 is equal to sine of 60 degrees times 1.15, which is equal to 6 sine times 1.15, 1 meter, which is an interesting result, which shows that an object which was which started down 1 meter up a 30-degree slope, slides down, and if there's no friction type forces involved, it turns around smoothly, goes up a 60-degree slope, and it reaches the same height, the same elevation as it had before on the upside. When we study energies, this answer of course will make perfect sense, but I just wanted to walk you through the mechanics of working through one of these kinematic equations. Now let's do a second example. This is another example that I covered in the class. We have a ball A rolling down a frictionless horizontal surface at a speed of 1 meter per second. So that's a simple scenario to depict. Let's call this position X, that's the origin, and this is ball A. Okay, and it's rolling down, it rolls along a frictionless horizontal surface at a speed of 1 meter, so it has velocity A of 1 meter per second. It's a constant velocity, so its acceleration is 0 meters per second squared. Ball B, we have another ball which is released from rest at the top of a 2 meter long ramp. Okay, so let me draw. So our ramp is 10 degrees, and here's ball B. Now it's released, which means that velocity B initial is 0 meters per second. Okay, and this whole ramp is 2 meters long, so I'm going to choose the x direction for ball B to be in this direction. So this is 2 meters down there, if this is in meters, and this is my 0, of course, origin. And as far as acceleration goes, well, there is G acting on the ball B, so you care about the component of G along the motion, which is, this is A acting on B, which is equal to G sine of 10 degrees, and it's positive because the acceleration vector is pointing in the positive, towards the positive end of the axis. Now the question is, will ball B overtake A before reaching the bottom of the ramp? The ramp is 2 meters long. Okay, how do we go about solving this problem? Well, we have written down in the information that we know, most of it anyhow. So let us work it out like this. We can say that, well, when ball A reaches ball, or when ball B reaches ball A, let's say that they both, when ball A is over here, then ball B is over here, so this displacement, which we can call delta XA, and then this is here, this displacement is delta XB. So ball A or ball B reaches ball A when the displacement A is equal to delta XB. Okay, so what is displacement? Displacement is area, and then let's say that this happens at time equals t, what shall we call it, t1. Okay, at t equals t1 seconds, the two displacements are equal, i.e. ball B reaches ball A after which it overtakes it. Um, so delta XA is the area on the velocity A dt, or the integral of velocity A dt from time equals 0 to t1, right? And VA is constant, therefore this is a simple integral to evaluate. It's simply VA T1 rather. Now delta XB on the other hand is similarly, that's also integral of 0 to t1 of velocity B dt. But notice velocity B is equal to velocity B initial plus acceleration of B times t. Now in the first case, since acceleration of A is 0, I did not consider the acceleration term. Okay, so this integral then becomes 0 to t1 of velocity B initial plus AB t dt. VB I is 0, so you can forget about that. So this simply becomes 1/2 of acceleration B t squared evaluated between 0 and t1, which is 1/2 of AB t1 squared. Okay, so if you now go back and look at the condition that we set here, when the two displacements are equal, when the two displacements are equal at t equal t1 seconds, we have this displacement for ball A, which is VA T1 is equal to the displacement for ball B, which is 1/2 of AB T1 squared, which means that if we simplify this a little bit, we can cancel that. VA is 1 meter per second, so we end up with T1 is equal to 2 divided by AB, and AB is G sine of 10 degrees, so this is 2 divided by G sine of 10 degrees seconds is when ball B reaches ball A, i.e. what is the displacement now when ball A reaches ball B? You can to evaluate that, let's simply take a look at the displacement of ball A. Its displacement was simply velocity of A times t1, which is equal to 1 meters per second times 2 divided by G sine of 10 degrees seconds, and the answer I believe is 1.174 seconds. At 1.1, oh, I'm sorry, this is meters now. At 1.174 meters down the ramp, ball B reaches ball A. The other way of looking at it is at 1.174 seconds after we release ball B reaches ball A. If you were to plot displacements versus time for ball A, we would have a linear slope like this. Why? Because we know ball A has a constant velocity of 1 meters per second, which is a straight line. Now ball B, which I'll show in green, will start as 0, so it's a flat line, and it speeds up and eventually catches up. Where the point that it catches up is when the two displacements are equal, of course. So at this point delta XA is equal to delta XB, as the graph implies too. So this is the time t1 that I was referring to earlier, when the two displacements are equal. Okay. Anyway, I wanted to work through these examples to hopefully clarify some of the use of kinematic equations. Notice that in using kinematic equations, I made sure that the acceleration is constant over the period of concern. Now, I did post the lecture notes for chapter 2. I'm going to post lecture note for chapter 3 sometime this weekend as well. I also did post a note on WebCT mentioning the quiz, the daily quiz that you're supposed to do on Tuesday. The daily quiz will be available sometime on Tuesday. Please log on to your WebAssign and it will say quiz 1. Work through quiz 1, and you only have one chance to answer those quizzes. It's not like homework where you're given multiple chances, so there's only one chance per question, and you need to complete it sometime on Tuesday. Please have a good weekend.